Hello everybody. Now we are going to discuss the next topic, that is design of the flywheel ring. In this topic we will design the flywheel ring. Okay. So this is the circle you can see. This is basically a ring. Okay. This is basically a flywheel ring. So we have to study about this flywheel, and if this is the center, let me draw the differential element here. So this is the center of the ring, and I am going to consider the differential element. Okay, and the differential element which is having the center, this is basically a center O, and differential element means this is the angle I am considering d theta. I am considering this angle as d theta. Okay, if this is the radius r, if this is the radius r of the ring, so I am just going to consider this differential area. Here you can say this is the ring flywheel. This is a ring, or you can say it is a flywheel ring also you can say. So we have to consider the differential element like that. Okay, this is the differential element I am going to consider here. So this would be the flywheel ring differential element having the angle d theta. So if I divide this differential element into two parts, so it would be like that. Yes or no? I am just dividing the differential element into two parts. So this angle would be divided also into two equal parts. That means it would be d theta by 2, and it becomes d theta by 2 also. Okay, d theta by 2 and d theta by 2. We all know that if the wheel is going to be in a rotations, so when the body is in a rotations, so there will be a centrifugal force working on that. Okay, so that would be, and that is working along the radius of rotations, and the direction of the centrifugal force would be like that. Okay, and what is the magnitude? Because this is the differential elements, you all know that the centrifugal force is equal to mr omega square. This is the general formula for centrifugal force, but we are discussing about the differential elements. So it would be dm r omega square, because radius and the angular velocity of the flywheel ring is constant. Okay, that means, I mean, the angular velocity is constant, but radius would also be constant, because we are considering at the outer sections, because this is working on that point, and the radius of this is capital R. Okay, the radius is capital R. So that this is that basically dF you can say. Okay, if you want to write the differential centrifugal force, that would be dmr omega square. Are you getting my point? So if this is the dmr omega square centrifugal force, so there will be a tension which has to be developed in the ring. Are you getting my point? So there will be a tension which has to be developed inside the material of the flywheel ring. So we can say this would be the tensions. Okay, you can see here, when the ring is going to be rotated, there will be a tension which is working along the periphery of the ring. So this would be the tension T, and the tension T would be here same. Okay, so this is T and this is T, and we know that this is the d theta by 2. And if you draw the tangent, like that, if you draw the tangent here at this point, you will get, because this is the differential element, so we can consider this angle as d theta by 2. Similarly, this is a tangent, so we can consider this angle as d theta by 2. This angle as d theta by 2. You can see here, this is d theta by 2. So it would be t cos d theta by 2, and this also be t cos d theta by 2, and both will be cancelled out to each other. Yes or no? This is t cos of d theta by 2, and this will also be t cos d theta by 2. So both will be cancelled out to each other because both are in the opposite direction. Okay, but it is having another component towards the center of rotations. This tension T having two components because this is the force. One component is in the horizontal directions and the second component would be in the perpendicular directions, like that. So both the components will be added. So this would be 2t sine d theta by 2. We know that d theta is very small, so we can say 2t sine d theta by 2, that would be equal to dmr omega square. We have to equivalent the vertical force balance because there is no unbalanced force here in the horizontal directions. Summation of force is equal to 0 here, and here that would be the 2t sin d theta by 2 would be equal to dmr omega square. Are you getting my point? So from here we know that sin d theta by 2 can be written as d theta by 2 because d theta is a differential angle, or you can say the very small angle. So this would be 2t multiplied d theta by 2, that would be equal to dmr omega square. We all know that m is equal to density into volume. Density into volume. Okay, so we can write dm as rho multiply volume. What would be the volume of the flywheel? Area into length. And what is the length? This is completely element. We are going to consider this complete element. So the area multiply r into d theta. R into d theta. We are considering this complete element. So the differential element, we have considered this differential element. So the volume of the differential element is area multiply r d theta, because we have to consider this length. Okay, we have to consider this length. This is the length of the flywheel here on the periphery. So density multiply area multiply r into d theta. Are you getting my point? So you just have to replace this value here. So you will get rho multiply area multiply r d theta multiply r omega square. From here you can get the value of t upon a. So d theta by 2 and 2 will be cancelled out and d theta will be cancelled out. Here the term remaining t and the area will be in denominator here. We just replacing the area from the numerator to the denominator in the opposite side. So that would, you will get rho r square omega square. R square omega square. And we all know that v is equal to r into omega. So we can write it as rho multiply v square. So now the important relations has come here. This is basically a hoop stress. This is denoted as the hoop stress here. Hoop stress sigma would be equal to t upon a. That would be equal to rho v square. This is very important relations we got here. You must remember these relations directly. Okay. So now, if you want to calculate the value of velocity from here, you can rearrange these equations. You will get the value of velocity in terms of hoop stress, rho upon sigma. This is also important formula. Okay. This is r omega. This is also important, and this is very important relations. So this is the basically hoop stress, and we know that hoop stress is less than equal to bearing strength of the flywheel. This is the bearing strength of the flywheel. This is the bearing strength of the flywheel. Okay, so here if it is less than equal to sigma b, that means the maximum value of sigma would be sigma b, yes or no? The maximum value of hope stress would be equal to sigma b. So if you write the sigma b, you will get the value. If you write the sigma b, you will get the velocity value, that would get sigma b upon rho, and this velocity would be the maximum velocity. This velocity would be the maximum velocity because sigma b is the maximum hoof stress. Okay, so here this is the another relations we got here. This all the relations you must remember directly. Now at medium speed, now just remember this, at medium speed, that means if the flywheel is having the medium speed, the flywheel is having with the spokes, the shape of the flywheels I'm talking about. So the flywheel with spokes. There will be a spokes in the flywheel when there is a medium speed. If you use flywheel at medium speed, the flywheel with spokes will be there. You can use flywheel with spokes. Okay, but at high speed, at the high speed, the flywheel would be disc-shaped flywheel. Disc-shaped flywheel. Disc-shaped flywheel. For the high speed, you can use disc-shaped flywheel. So let me draw the diagram here. Rough diagram I'm going to draw here. If this is a flywheel and the flywheel with spokes means like that, the spokes will be like that. Okay, so this will be the flywheel with spokes. It's used for medium speed. Flywheel with spokes. And now, if in the question it is asking at high speed, we all know that at high speed, disc-shaped flywheel would be used. So, what is the shape? Actually, disc-shaped means what? This is basically the disc-shaped flywheel. Let me tell you the important thing about the disc-shaped flywheel. So, this is the disc shape means it is completely having the shaded area, and if you see the disc-shaped flywheel from the side, you will get the shape like that. This is basically a side view of the disc-shaped flywheel. Okay, this is basically a side view of the disc-shaped flywheel. That means this is having the maximum cross-section area at the outer sections, and at the midpoint there will be a minimum cross-section area. Okay, so this is used for high. This is used for highest energy storing capacity. This is used for highest energy storing capacity. So this is the disc-shaped flywheel. Okay, and this is the best flywheel. Best flywheel. Flywheel, disc-shaped flywheel is the best flywheel, and it is having the highest energy storing capacity. Are you getting my point? Highest energy storing capacity. If you want to find out the highest energy storing capacity, so it would be equal to the half I omega square. This is the highest energy storing capacity. You can calculate using this formula, half I omega square. Okay. Now this was the design of the flywheel. I hope you will able to understand how to design the flywheel ring. We will do the numerical questions on this, so it would be easy to understand. Now let me tell you fundamental equations of the flywheel so that it will be important for the numerical problem, so you will not be get any confusions. So I'm just writing here the direct values of the mass, that means the moment of inertia of the flywheel in different case. So fundamental, according to the shape of the flywheel, fundamental equations of flywheel. This is a small topic. We all know that m is the mass of the flywheel. If m is the mass of flywheel and k is the radius of gyration, this is a small k. This is not r, this is a small k. This is the radius of gyration. This is the radius of gyrations. Okay, so we can write that moment of inertia would be equal to mk square. This is the mass moment of inertia, that is equal to mk square. The k value, now I'm going to write the value of k. K would be equal to r, radius. I'm talking about radius. This is the radius of gyration, small k. If k is equal to r for ring, you can write that for ring, radius of gyration is equal to radius of rotations, and then I would be equal to, that means mass moment of inertia would be equal to mr square. That is valid for ring. Okay, so in the second case, for the disk, if the disk is given in the question, you just have to find out the radius of gyrations, that is equal to r by root 2. So you will get the value of mass moment of inertia, that is mr square by 2. Okay, so this is for the rim and for the disc. Basically the flywheel is having two shapes, ring and the second is disc. So you can put this value in order to find out the mass moment of inertia. Just remember that this k, small k, is denoted as the radius of gyration. Okay, so I hope you will able to understand this design of the flywheel ring.